This paper presents a non-invasive, vision-based approach to measuring the velocity of a skeleton athlete during the critical push-start phase of their run. Skeleton is an Olympic winter sport in which an athlete rides a sled head first down a twisting course of ice. It is closely related to the sports of bobsleigh and luge, and as with those sports, the overall performance of the athlete is greatly affected by how much speed they can produce during the initial start phase. At the start of a skeleton run, the athlete will push the sled along the ice while sprinting, and then choose the optimal moment to launch themselves onto the sled and continue the run with only gravity and their skill at steering to guide them to the finish. Athletes who can maximise the speed they achieve during the start will have the advantage of carrying that speed into the rest of the run. It is therefore of interest to athlete and coaching staff alike to monitor performance and fully understand the effect of training programs and technique changes. Ideally, any measurements must be made in a non-invasive way so as not to interfere with training or cause an alteration in the way the athlete performs. Video analysis has the potential to satisfy the needs for non-invasive measurements of velocity and athlete biomechanics thanks to recent progress in human pose estimation. It remains to be seen, however, whether these new systems can achieve the desired levels of accuracy. For an initial study, this paper limits itself to the basic measurement of athlete and sled velocity on a push-track training facility. The training facility consists of a concrete track with metal rails on which a wheeled sled can run and athletes can focus on their sprinting and loading technique. It is envisaged that future work will be able to consider more advanced biomechanics measurements that are otherwise only possible with marker-based motion capture systems. For this study, an arrangement of 9 cameras was installed along the push-track training facility to capture the first 8 meters before the athlete loads onto the sled. 7 cameras looked perpendicular to the track, and the remaining 2 cameras were positioned to look as parallel to the track as was possible. This camera arrangement was intended as a balance between the desire to cover as much track length as possible while retaining the advantages of overlapping camera views and managing limited space. The cameras were frame synchronized through an external trigger and set to record at 200 frames per second. The camera system was calibrated by walking a circle grid calibration board through the scene, making sure that the board could be seen by multiple cameras at any one time. The final calibration was achieved through a bundle adjustment of board observations. An estimate of the ground plane was used to set the origin and orientation of the calibration. Our approach to measuring athlete and sled velocity consists of 2 software systems. The athlete is initially detected in the images using an off-the-shelf CNN-based human segmentation algorithm, which labels pixels as belonging to various human body parts including head, torso, legs and arms. Bounding boxes for the head and torso are then recovered from each individual camera view and a robust occupancy map algorithm used to initialize 3D position. This initial 3D estimate is then refined through an optimization process, and a Kalman filter is used to achieve a smooth track. The sled is tracked by using transfer learning to teach a CNN to detect the corners of the sled. Detections in individual camera views are then robustly fused to produce the 3D position estimate that is tracked over time. The velocity of the athlete is taken as the velocity of their centre of mass. It has previously been shown that the centre of mass can be estimated using voxel hulls, but robust voxel hulls require an optimal camera layout, and the pose and motion of the skeleton athlete makes this difficult without using an excessive number of cameras. The centre of mass could alternatively be inferred from 3D pose estimates, and recent literature has suggested various methods for human pose estimation. Joint detectors such as open pose provide limited information about the volume of the athlete and can result in quite noisy tracks. Systems like Vibe, which generate 3D pose from single camera views, have no clear solution for fusing the estimates between multiple camera views and were also noisy when tested. We suggest that it is sufficient to estimate the 3D bounding box around the head and torso of the athlete to recover a reliable estimate of athlete velocity. By using a CNN-based human segmentation algorithm, both the location and size extents of the body parts can be determined. For this work, the 2019 human segmentation algorithm of Lin and colleagues is used. The segmentation can be imperfect, resulting in partial, broken, missing or mislabeled segmentations. As such, a robust solution is needed to fuse the camera views together. To this end, a variant of occupancy maps is used for the initial detection of the head and torso. Bounding boxes are placed around each detected head and torso region in each camera's segmentation result. Next, the ground plane is divided into a grid of square cells. Each cell is taken in turn and projected into each camera view. If the projection of the cell lies between the horizontal extents of any head or torso bounding box, the occupancy of that cell is incremented by 1. The initial 3D estimate of the head or torso is found at the highest peak of the occupancy map. The result of this process is a robust method for initializing the head and torso position estimates in each frame. The head and torso are modelled as 3D axis-aligned bounding boxes. Given an initial estimate of the position of the head or torso, the optimal position of the bounding box in 3D can be computed by minimizing an error term using information from all cameras. To make this as simple as possible, the error term is based only on the intersection of 2D bounding boxes and the distance between 2D bounding box centers. First, the initial 3D estimate is projected into each camera view, providing bounding box B initial. To handle broken or partial segmentations, any detected regions of head or torso which overlap with B initial are merged into a single bounding box, A. The optimization then adjusts the position of the 3D estimate to maximize the overlap in each camera view while minimizing the distance between bounding box centers. The optimization can be carried out using any nonlinear optimization library. A Kalman filter is used to produce a smooth track of the head and torso over time. To detect the sled, Deep Lab Cut was used. This is a system for transfer learning, which allows a pre-trained convolutional neural network to be specialized for a novel detection task. In our case, the network was specialized to detect the corners of the sled using a small subset of the available video data. The resulting network was able to detect the sled corners, but might not always detect all corners in all views or correctly identify which corner was which. As such, fusion to get a 3D sled position estimate was designed to be robust against the observed detection errors. The sled corners are back projected to the known height of the sled. This produces clusters of 3D points. Using the known orientation of the sled, it is possible to know whether each cluster represents a left or right sled corner. The final labeling of corner points is determined by testing all possible configurations of sled position and identifying which is the most consistent with the available data. The final sled position is determined by minimizing the distance of each back projected corner detection with the associated sled corner. To test the performance of the system, 33 push trials from 12 athletes were recorded using both the proposed vision system and a marker-based motion capture system. The marker-based data was processed using gold standard biomechanics practices to determine athlete and sled centers of mass and velocities. The results show that the proposed vision-based system, which requires no markers and no interference with the athletes, produced measurements that were highly consistent with the marker-based ground truth. We have proposed and evaluated an algorithm to measure the velocity of a skeleton athlete and their sled during training for the critical push start phase of a run. Our non-invasive video-based system was shown to be capable of making measurements that were consistent with a gold standard marker-based motion capture system. In comparison to existing technology at the training track, such as laser timing gates, the proposed vision system offers a dense measurement of velocity. The video-based solution also offers the future prospect of making detailed biomechanics measurements of the athlete during the push and loading phases. Future work is expected to consider deployment of this system, trials of the system on real ice courses, and measuring athlete pose.